welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're starting the final chapter of our notes. It's on spectral statistics. So far in this course, everything we've done has been from the time domain. That is, we're looking at time series from the perspective of time, which makes a lot of sense. But whenever you have a signal in time, you can also flip it on its head, and you can consider the frequency domain. And that's what we're going to be doing in today's lecture. We're going to be considering the frequency way of analyzing time series data. We're going to start with the concept of a periodic process, which is a lot like it's a stationary process. It is, in fact, stationary, and it's just going to be a little bit different, and it's going to allow us to figure out what frequencies are most powerful or most significant in our time series data. So, how are we going to deal with all of this? Well, let's go take a look at the notes and find out. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to start the last section of the course, at least the last main section. Maybe if there's extra time, we'll do a couple bonus lectures. But the last main section is what we're going to be talking about is analysis of time series in the frequency domain. This is spectral methods, because we have a signal in time, right? We have time series data. Now, if you've ever seen anything about signals processing, you know that you can always look at a signal in the time domain, as we've been doing for this entire course, but you can also flip it on its head and look at it in the frequency domain, and it will give us another lens to look at our time series data and to try to understand what's happening with it. This is specifically useful when we have periodic fluctuations in our time series, specifically things that we looked at before, like in our seasonal ARIMA models, because when we have in a seasonal process, we have this periodic sort of fluctuation. And if we're looking in the frequency domain, we can see that kind of lighting up at certain. We can see the periodicity lighting up at certain frequencies. So, how in the world are we going to do this? Well, we're going to have to use some tools like the Fourier transform. So it's a pretty good area to study, and let's get into the notes and jump right into it. All right, so this is going to be the beginning of the frequency domain section. Now, the first thing we're going to talk about is the idea of a periodic process. So we're going to reconsider our time series, but using a different, say, basis for representing it. But first, I want to use the notation that we will use omega to be a frequency. So, for example, omega equaling 1/12 is kind of like a per month frequency. So this is something we might see if we have data that it has a month or an annual, I should say, a per month frequency, I guess, of 1 year. Maybe that's a confusing English thing to say. Basically, the idea is that if we have monthly data and if it repeats itself every year, if there's some annual cycle to it, like let's say temperatures, if we take the average monthly temperature and we look at it for years and years, we would expect there to be a cycle of length 12 hiding in our data. That means the frequency would be 1/12. And it's something that we could use, again, spectral methods to try to detect that in our data. All right, so what we're going to focus on in today's lecture is the idea of a periodic process. So the periodic process I'm going to write as X transpose is equal to A, some constant or some coefficient amplitude, times the cosine of 2 pi omega t plus phi. Now, phi is kind of unfortunate. It's the phase, and I know phi is usually our autoregressive parameter. Phi is going to disappear in a second when we use some trig identities, so we don't need to worry about that. But just in general, right, if we represent xt like this, what we have is we have A is the amplitude, there we are. We have, of course, omega is the frequency, t is the time, phi is the phase. So this is just going to be some, I guess, periodic signal where the phase phi offsets the signal in time, right? This is all in t. So this is still t. And this would be, I guess, I'm not even sure what the vertical axis would be, but A, the amplitude is going to tell us like how strong our signal is, right? This is A, and the offset, where would the offset be? I guess the offset would be from like here to here would be phi. Right, so phi again shifts it, A, the amplitude makes it bigger or smaller in height. Now, what we're going to do is we're going to rewrite as xt is equal to u1 times the cosine of 2 pi omega t plus u2 times the sine of 2 pi omega t. So now we have a linear combination of a cosine and a sine. And if we, I guess, recall our trig identities, I can say where u1 is going to be a times, I think it's the cosine, yeah. Do I remember my trig identities? I hope I do. Right, u1 is going to be a times the cosine, and u2 is going to be a times the sine, but I think there's a minus sign there. Yes, there's a minus sign there. Right, this comes from the trig identity that the cosine of x plus y is equal to cosine x cosine y minus, not cosine, minus the sine of x and the sine of y. All right. So what we're going to do is we're going to think of u1 and u2 as uncorrelated mean zero random variables, and now we have a random process. So basically, if u1 and u2 are uncorrelated RVs for random variables, then we have xt, I guess, some sort of random process. It's not that interesting right now. It's just we have a random coefficient in front of the cosine and a random one in front of the sine. So not that interesting yet, but it will be in a second. At the very least, what we can do is if we treat u1 and u2 as, again, uncorrelated random variables, then we can do things like we would do with random variables, like compute an autocorrelation. So if we, I guess, we also need a variance. Our uncorrelated random variables, we'll say such that the expected value of u1 is equal to the expected value of u2 is equal to 0, and the variance of u1 is equal to the variance of u2 is equal to sigma squared. So from here, we can actually compute the autocovariance of x, because x is still a, I guess, a time series at some sort of stochastic process in t, and we can consider the autocovariance at a lag of h. So in this case, what we're going to do is just write out the whole thing. It's a little messy, but it's perhaps the best way to do it. We're just going to get, well, u1 cosine, I think we'll do it that way,
2 pi omega t plus h plus u2 sine 2 pi omega t plus h, comma, and then the other thing we're going to get is u1 cosine 2 pi omega just a t, no h, and a u2 sine 2 pi omega t. And yeah, we want to compute that thing. Luckily, we can, well, first, I guess, break things up. We can break things up over the, I guess, using the fact that the covariance is a bilinear form, so we can break things up over the addition signs. And because we know that u1 and u2 are uncorrelated, we only have to consider when u1 is paired with u1 and when u2 is paired with u2, because otherwise the covariance will be 0. What I mean by that is we'll have 2 pieces rather than 4. We'll have the covariance of u1 cosine 2 pi omega t plus h and u1 cosine 2 pi omega t. And we're going to add to that the covariance of u2, not cosine, u2 sine 2 pi omega t plus h, u2 sine 2 pi omega t. Right, and again, the other cross terms have to be 0 because u1 and u2 are uncorrelated. Now, in this case, because we just have, well, that their mean 0, and the only thing that's random here are the u1s and u2s, this quickly turns into just being sigma squared times, I guess, the cosine 2 pi omega t plus h. There's a lot of trig that's coming in equations in this section. Cosine 2 pi omega t plus, nope, I think it's a, is it a plus? I thought it was supposed to be a, oh no, it is a plus, yeah. Plus sine 2 pi omega t plus h. Let me double check that. Actually, no, there's a typo I have. I was thinking there's a, I mean, yeah, there is a typo here. Nope, never mind. There isn't, because I was getting confused with the fact that we have a minus sign here, but the minus sign is absorbed within the U2, so it's not really there. I was worried that I forgot a minus sign. But I think we're good. So we'll just keep pushing forward with another sign, 2 pi omega t. And if we trig identity it, we should be able to get something that looks like sigma squared cosine of 2 pi omega h, no t. So what this means, so this is actually quite interesting. So what it means is a couple things. First of all, well, the autocovariance will fluctuate in h, right? Cosine kind of starts up and goes down and then goes up and then goes down. So our process will go from being highly correlated to not correlated to negatively correlated to 0 to high, positive correlation and so on. But furthermore, there's no t here. Therefore, it's stationary. And that's good times, right? Because we like stationary processes. So this is another type of stationary stochastic process that you might see. Now, again, in this case, it's not the most interesting because we just have 2 random variables, a u1 and a u2. But we can extend this to more complicated stochastic process. And what we can do is, I'll say, to make this more interesting, we can consider frequencies, omega 1, I think I was using Q, right, as my index, yes, omega 1 through omega Q. And then we can write down a more interesting periodic process that is going to be the sum J from 1 to Q of, well, two things, I guess summed up Q times, which is going to be UJ1 cosine 2 pi omega J T plus UJ2 sine 2 pi omega J T. All right. Oh, yes. With, as before, UJ1 and UJ2 mean 0, uncorrelated random variables. Oh, yes. And with uncorrelated mean 0 random variables with potentially, yeah, and they could have different variances with variances that are sigma squared J, yes. So the point is that UJ1 and UJ2 have the same variance and are uncorrelated, but we might have UI1 and UI2 where you have a different variance, still uncorrelated, but you have a different variance there. And then we can compute the autocovariance of this new, more general periodic process X, and it's going to be kind of the same thing as above, but if we just do it, I guess, Q times, well, we're just going to sum up Q of these things. Thanks to, again, linearity, or I guess bilinearity of the covariance, we can get away with, well, this. The cosine of 2 pi omega JH. So our autocovariance now is going to look like a sum of a bunch of cosines with various frequencies. And this is nice because then you could have multiple different signals with different, or I should say multiple frequencies on top of each other within the same signal. And that's kind of neat. Now, oh yeah, there's one little issue that we have to mention. I'll say warning. Maybe we'll do it in red because red is a good color to write the word warning. Warning. There could be aliasing. Aliasing when I'll say discretely sampling xt. So, okay, what are we talking about? Well, what we're saying is that we have this idea of a general periodic process xt. In some sense, t is continuous, but when we take time series data, we're going to be sampling it at in this course, a fixed in a uniform rate. Now, the sampling rate can affect what the process looks like from the data. And this is the idea of aliasing. So aliasing in this context, you've probably heard of it if you ever have done either graphic design or if you're a gamer and you know about anti-aliasing for GPUs, or I guess if you do like audio engineering, aliasing can come up all over the place when you have discretely sampled things that are trying to be turned into, or discretely sampled things from what is otherwise supposed to be a continuous object. Right, so the idea of aliasing is simply that a high frequency may look like a low frequency if sort of sampled discretely. What it means is that sometimes you get two different frequencies that might look the same in your data because you don't have enough sample points to disambiguate them. So the example that I have in my online notes that I plotted nicely, and I'm going to draw here, and hopefully it doesn't look too messy, is that imagine we have some signal that's just fluctuating up and down at a nice high frequency periodic rate like this. That's not so bad. Let's see if I can draw the next part. But now let's say that we're going to sample, and this is, let's say, the t-axis, and we want to sample this at some discrete time. So we sample and we sample and we sample. These are supposed to be equally spaced. So let's pretend they're equally spaced. And we sample and we sample and we sample, I guess, something over here. Okay, it's not exactly perfect, but the idea is that when you try to reconstruct a signal from my sampled points, it might look like a low frequency wave, where in fact what you have is a high frequency wave. You're just not sampling it fast enough to be able to detect that. So this is the idea of aliasing, where you basically have this overlap of a low frequency and a high frequency that both would give you the same looking data. So it's just something to be aware of when you're dealing with time series and you're specifically with periodic processes and signals analysis. But anyway, okay, so we have the idea of a periodic process, right? I'll highlight it in green because it's going to be kind of. So this is the kind of thing that we would want to, say, try to fit to some data, right? What we have is we have a model for a time series xt. If we have data xt, we might want to try to fit coefficients uij1 and uj2 to some data and see what we get. Well, we can do that. And now we're going to do regression and the Fourier transform. I'm not sure if you actually do the Fourier transform in a undergrad statistics degree. I mean, if you took a math like pure math probably talks about the Fourier transform, but I'm not sure where exactly it would show up. I mean, it could show up easily in, say, a course in analysis or measure theory, but that would probably be saved for more advanced. I guess it could show up in other areas too, like applied math. So anyway, the Fourier transform, super important, and it allows us to switch from time to frequency domain and back again. And we'll also talk about the fast Fourier transform because, yeah, actually computing a Fourier transform can be quite computationally tedious. Anyway, yeah, so let's say given a time series, which is going to be x1 through xt. And then just for convenience, we're going to say with t being an odd number, because otherwise we're going to have one extra term, which I'm going to write down in a second anyway. But for t being an odd number, basically we can write our process xt as a linear combination. So we're going to get beta naught, that's our intercept term. And then what we're going to have is we're going to have a summation, and this summation is going to be from, man, my notes need some patching up. I'm going to try to get that done. It's going to be a summation from 1 to t minus 1 over 2. And here we're going to have a beta j1 cosine 2 pi t times j over capital T. That's going to be our frequency, beta j2 times the sine of 2 pi t j over t. There's our frequency again. Right, and the idea is that this, if we can basically, so note that the cosines and sines form a basis. What's that mean? Well, i.e., we get a regression that perfectly fits the data. Now, if you recall from regression class, we typically don't want to perfectly fit the data with a regression, but the idea here is that what we can do is if we have enough cosines and sines, we can accurately reconstruct all of our data points, and I guess if we treat t as continuous, we can interpolate between them. The data points. This is like a high degree polynomial. So remember, if we have a really high degree polynomial, we can fit it exactly to all of our data points. Now, we don't want to actually do that with linear regression, but the point is that we could. If we have t data points, then if we have a t minus 1 degree polynomial, it will go through, well, we can find a t minus 1 degree polynomial that will go through all of our data points. And similarly, we can do the same thing with cosines and sines because they form a basis here. So again, this is just the idea that we can in some sense try to get coefficients, and these coefficients beta will correspond to different frequencies. And that's going to be, interesting in a moment. But we also have to do one more thing, which is figure out what happens if t is even. Well, then we get a slightly different thing. We still get our beta naught. We still get our sum j from 1 to t over 2. It's slightly different now. T over 2 minus 1 of beta j1 cosine 2 pi t j over t plus beta j2 sine 2 pi t j over t. But we're missing one extra thing, and that one extra thing is going to be plus beta t over 2 cosine pi t. So we get one extra beta floating around if we have t being even by itself. Otherwise, they all pair up inside this summation. All right, so then the question that we're faced with is, why are we writing a time series in terms of some giant linear combination of trig functions? So it's always good to ask yourself, why are we doing this? We're doing this because any large, say, significant betas will correspond to a prominent frequency cycle in our data, our time series data. So what that means is that if we were to actually try to fit one of these giant trig polynomials, say, to our data set, then we're going to get a bunch of coefficients beta. And if we see any really significant or very large values in magnitude, large values of beta, that tells us that that frequency That is, specifically, that J over T frequency is somehow prominent in our data. So basically, we can think of this as one big linear regression problem, where the design matrix, there's going to be a design matrix that corresponds to all of the betas here. We have our intercept term beta naught, and then we have a whole bunch of betas in our summation here. All right. Okay, so there's a bunch of different trig identities we can use to help sort out what's going on with our design matrix. So, right, typically, we would have something like beta hat is equal to x transpose x, x transpose y, where in this context, X is a design matrix and Y is actually going to be XT, the data, the time series data. So it's not the best notation to use because it conflicts with what we had before, but just recalling what we would do in linear regression class. Oh, I forgot my X transpose X inverse. There we go. But it turns out that things are actually a lot simpler here, because in this case, the design matrix has orthogonal columns, and that's always a good time. That's basically what I do all in the design of experiments course I'm teaching, right? The whole idea is, well, if we have orthogonal columns, that's great for estimating different, I guess, terms in an ANOVA table, for example. But anyway, in this case, we can show that. Now, I don't want to go through all the tedious equations to actually do that, but roughly, actually, we're going to just stop and I'm going to copy them right over because I don't really want to write all these out. And with the magic of video editing, we're back and we have all of the equations copied right here, so I don't have to write them out by hand. It's wonderful. Because they're not the most interesting things to look at, but basically what we're trying to get at is that if we take a column of our design matrix and do a dot product of it with itself, what we're going to get, why is it not switching my color? Man, Microsoft, fail again. Well, I guess we're doing the whole thing in black, unless I can change the main marker, but OneNote decided that I can't change to a different one because it seems to think I'm trying to be an eraser. Well, we'll just go with it. Oh, Microsoft. Anyway, what we have here is that we have our columns of our design matrix, and if we do a dot product of a column with itself, what we end up with is an n over 2. Unless, where is it? We specifically have the case where j is equal to 0 or j is equal to t over 2. In the case that t is even, in that case we get an n for the cosine bit, and we get a 0 for the sine bit. This is actually the reason why we, well, no, never mind, forget that. Yeah, and then every other dot product of columns is going to get us zeros here. Right, so what that means is we have an orthogonal design matrix. There we go. So we have an orthogonal design matrix, and that means that computing beta hat is simpler. So rather than having to compute x transpose x and then invert a giant matrix, which, as we've talked about in the case of forecasting, we don't want to invert a giant matrix if we can avoid it. So let's not do that. Instead, what we can do is we can basically identify that beta hat j 1 is going to be 2 divided by t times the sum t from 1 to capital T of x t times the cosine of 2 pi t j over t. And the beta j2 is going to be the same thing, but it's going to be for the sine x transpose times the sine of 2 pi t j over t. And this is specifically for j not equal to 0 or t over 2. In those cases, we have a specific, this is important and this is important, and then we have two specific formula, which is beta hat 0, that is, right, if we're trying to estimate the intercept term, what is it going to be? It's the sample mean, x bar just equal to 1 over t, sum of the x little t. And lastly, if we want to estimate beta t over 2 for even values of t, then what we end up with is a 1 over t times the sum of what? T from 1 to capital T of an alternating sign minus 1 to the t x t. So these formula, again, might be a little confusing at first, but just, I still can't change my marker, because of course I can't. Oh, Microsoft, you're killing me. Just killing me. All right, fine. I guess we're just going to have to do the entire lecture with no extra colors, so it makes me a little bit sad, but we can get through this together. All right. What I was getting at is that in linear regression, in simple linear regression, what we have is we have that, y is equal to beta naught plus beta 1 x plus epsilon. And if we want to estimate beta hat 1, what we end up with is something that's going to look like the sum of yi times xi divided by the sum of xi squared. So here, the yi are actually corresponding to the xt, the data points, and the xi in linear regression are corresponding to the design points, the cosines and the sines. And the denominator ends up just being the, oh, here I used an n over 2 where I was supposed to use a t over 2. There's another typo that I need to go and correct. Anyway, that's what we have going on here. We basically have a linear regression setup, and what we want to do is compute this thing for all of the, j's, I guess, so all of the different frequencies, and then we can use that to get a sense of what frequencies are prominent in our time series data. And this leads to the idea of a scaled, not a sailed, a scaled periodogram. There's a lot more terminology in this section that's new. So the scaled periodogram is going to be P, and it's going to be P of J over T, where it's evaluated at a specific frequency, which in this case is going to be omega being J over T. And what it's going to be is the sum of the squared coefficients J1 and J2 squared. Can't change colors. Anyway, if basically if this is big, then J over T is a significant frequency in the time series, TS. Okay, so, all right, I'm basically just saying we have some function of the frequencies, and it's going to give me the squared sum of the two coefficients here. But this is going to be important because we can use the discrete Fourier transform to compute all of these. Oh, yes, and one other key thing to note. Also, this Pj over T is the variance for the, well, it's basically the variance for the jth frequency, for the J over T for beta J1 cosine 2 pi T J over T. This isn't exactly the right way, I think, to write it, because technically it's not a random variable, so I should probably rewrite this slightly, but you can think of it as a decomposition of the variance for different frequencies. So if we have a bunch of variation in our time series data, we can attribute that variation to each of the different frequencies from 1 over T, 2 over T, all the way up to, I guess, T minus 1 or T over, I guess it's T minus or 1/2, which would be T over 2 over T. So the T's cancel out. Anyway, the idea is that there's going to be kind of a way to think about the scaled periodogram as the variant of our time, of the components of our time series. All right, so next is computing this for large T is not feasible. So what we can do is we can use the Fourier transform if T happens to be what they call a highly composite integer. So, but if T is highly composite, which basically means, i.e., it has lots of small prime factors, e.g., let's say 2 to the, I don't know, what's a good number? 2 to the 10 would be 1,000, or no. Yeah, 10 to the, we'll do 2 to the 10 equal 1024. Yeah, so for example, if it's just 2 times 2 times 2 times 2 times 2, then it has, well, lots of small prime factors. In that case, I didn't finish this sentence, but if T is highly composite, then we can use the discrete Fourier transform, or DFT. So what's the discrete Fourier transform? Well, the discrete Fourier transform basically says I'm going to compute a D at JT, at frequency J over T. And what that's going to be is something that's going to look like 1 over the square root of capital T times the sum T from 1 to capital T of x T e, the exponential, of minus 2 pi I T J divided by T, where I here is the imaginary number I, and J is the corresponding I guess, corresponds to a frequency. Now, why are we writing this? Well, if we write this out, remember we have a complex exponential, and e to the I theta is going to be, okay, I can manually change the color, right? I'll say recall that e to the I theta is going to be the cosine of theta plus I sine theta. Now, the one peculiar thing is that sometimes the coefficients will change or the scaling will change in the discrete Fourier transforms. Well, yeah, you always have to be a little bit careful with the specific implementation or the way that the Fourier transform is written down. But if we define it like this, then what we end up with is we can rewrite this summation as a sum of two. Well, I guess we'll do it as one big sum. Why not? Xt cosine 2 pi t j over t minus I xt sine 2 pi t j over t. All right. I swear we're actually going somewhere with this. We're almost getting to what we want. Because what happens is if we have this setup, then therefore if we want to consider the squared magnitude or the absolute value of this thing squared, remember, this is a complex number. So the discrete Fourier transform is giving me a complex number. I've got my real part cosine, my imaginary part I times the sine. If I take the magnitude of it and square that, it's basically the Pythagorean theorem. What I'm going to be doing is I'm going to take the, I'm going to get a 1 over t because I'm squaring everything. And then I'm going to find the real part, and the real part is going to be squared. So what I end up with is the sum of all the real pieces here, the cosines that is, t from 1 to capital T x, t cosine 2 pi t j over t. The entire sum is squared. And then what I do is I add to that 1 over t times the summation of the second bit here, the sines. And remember, I'm taking a magnitude, so I drop the I and I'm squaring it so I don't have to wrap the entire thing in a square root. 2 pi t j over t, and this whole thing is squared. Okay, so this is an unscaled periodogram. That is still bugging me that I can't change the color without going through the menu. Right, this is what they call an unscaled periodogram. And if we were to write, then what we find out is that the periodogram P j over t is going to be 4 divided by t. To double check that to make sure that I'm yeah, I'll double check that in 1 sec. It's 4 over t times the squared magnitude d j over t squared. So if we go back up to what this thing is, right, the squared, let me make sure that we're doing this right. So the squared periodogram, or the scaled periodogram is the sum of the squared beta ji or beta j1 and beta j2. Now, beta j1 and beta j2 correspond to these guys up here. So if I square them, I should get something like 4 divided by t squared times the sum of this in this big sum squared. And that's where we would have a 4 over t squared. So when we, I guess, take this thing and multiply by 4 over t squared, we recover that. So we're good. All right, so this is what we want. And I guess we can say that this is going to be our scaled periodogram. And again, sometimes the definition that you might find in a given coding package might be slightly different, so you have to be a little careful how scaling is actually done. All right, so what are we doing next? All right, and we're back, and now I've actually been able to recover by resetting everything, the ability to change the color on my pen. So I'm happy again. Let's look at the last bit of this lecture. So what we have here, right, is the idea of that we can use. So what are we doing, right? Because sometimes when we just fight our way through all of these equations, it's like, what in the world is the point of all this? Well, the point is that, let's go back to the beginning. We have this idea of a periodic process. The betas are going to correspond to different frequencies. If the sum of the squared betas, that is, if my scaled periodogram is big, that tells me that that frequency is present strongly in my data. Now we can make that more precise statistically later, but that's just roughly the idea. Now, to actually compute all of these, if we go back up here, we don't want to actually have to compute all of this by hand because t could be really big. It could be like, say, 1,000, and j is going to run from, I guess, 1 to t over 2, right? Or t over 2 minus 1, depending on, or t minus 1 over 2, I mean, depending on if t is even or odd. Now, we don't want to have to compute all of these by hand. So what we can do is we could consider the discrete Fourier transform, because it turns out that if we apply the discrete Fourier transform, which just says multiply my data set xt here by a bunch of complex exponentials, and because we're defining it this way, we're going to scale it by the square root of the sample size. But really what it just says is take those data points, multiply by complex exponentials, sum it up. All right, and that's going to give us what we want. But then the question is, well, is that any easier than computing what we already had? And the answer is, well, not really, until we consider the fast Fourier transform. So what we want to do is we want to figure out, so the next is how do we compute dj over t quickly, right? Because so far we haven't really done much, but just notice that the discrete Fourier transform will give us what we want, which is kind of equivalent to just doing linear regression with all of these sines and cosines as our basis functions or in our design matrix. So there's a couple things to note first. So first, we want to note that the discrete Fourier transform is symmetric about t over 2, or sorry, about 1/2. So I guess, yeah, t over 2 over t. It's basically 1 minus j over t. The magnitude here is going to coincide with the squared magnitude of just j over t. This is because, why? Well, it's because trig functions, right? And trig functions say that the sine of 2 pi minus theta is equal to minus the sine of theta. And I think the cosine, is even. So the cosine of 2 pi minus theta is just equal to the cosine of theta. So if we square these things and sum them, the sine difference in the sine the plus or minus, the minus sign next to the sign will vanish anyway, so it won't really matter. So because of this, we can say, therefore, we only need to consider, I guess, d j over t for j from 1 to t over 2. That's assuming t is even. If it's odd, then I guess t minus 1 over 2. Or equivalently, we can just write j over t should be less than or equal to 1/2. All right. So what do we have? Well, the DFT is a big system of linear system of equations. Like everything seems to always be a big linear system of equations, mainly because if it's not a big linear system of equations, we're kind of stuck. At least in this case, if we have a linear system of equations, we know what we want to do. We just have to figure out how to efficiently solve it. If it's a nonlinear system, then we're kind of in big trouble, usually. So that's a good thing. We have a linear system of equations, and we're going to write d, which is the vector of, I guess, the discrete Fourier transform vector is as w times x, for d basically being our d 1 over t all the way up to whatever d. I'll just say 1/2 if we assume that t is even, but adjusted again if it's not 1/2. X is just our data set x1 through xt, and w is going to be some matrix. It's going to be our discrete Fourier transform matrix, which is going to just be, well, all of these sines and cosines that we have shoved in up here. Okay, so if we have that, what do we do? Well, the idea is that this matrix multiplication takes on the order of t squared time. So again, if t is a really big time series, we don't want to do this matrix multiplication. I mean, okay, computers are pretty fast. I guess if we really wanted to, and you could, I guess feasibly, you could parallelize this by applying x to each row of w individually. So yeah, maybe you can just kind of brute force your way through it, but we could be a little fancy and use something called the fast Fourier transform. So that's always nice. So instead, we could use the FFT, or the fast Fourier transform, which uses a sparse representation of the matrix W and runs in t log 2t time. So computationally, it runs a lot faster. It's now linear with this logarithmic term on it rather than t squared, which is going to be a lot bigger. But we need t to be a power of 2 for this to work most efficiently. Now, there's a lot that's gone into how to do fast Fourier transforms. People spend lots of time. There's more than one algorithm, but basically we'll consider the divide and conquer algorithm. I always say conquer or concur. Conquer with a Q. Yeah, divide and conquer algorithm, which is when t is equal to some big power of 2. It doesn't have to be big, I guess. It just has to be a power of 2 for some m. And the idea is what we're going to do is we're going to take our data and we're going to split it in half. And then we're going to split it in half again and again and again. And that's why there is a log 2t in the time, because what we can do is we can just, we can just split this up in sort of a binary fashion, which takes the time from t to log t for the second t and the t squared, I guess. Anyway, yeah, the idea is, i.e., split data into odd and even indices, which is going to be something like x1, x3, x5, etc., and x2, x4, x6, etc. So why does that matter? I mean, the idea is, right, if we have this, we can continue to split and split and split into our data in half again, and in half again. So it matters because we can rewrite the discrete Fourier transform as, well, scaling it by the square root of t, so I don't have to drag around a square root of t everywhere. We can write dj over t to be the sum t from 1 to capital T over 2, and that's going to be x 2t e to the, let's see if we can get this. Why don't we write it out? We'll write it out long form like this, so I have more room to write it all down. Minus 2 pi I j over t divided by 2. Let's write it all out and then see if we can make some sense out of this thing. Plus, and then we're going to have a coefficient of e to the minus 2 pi I j over t. And we're going to multiply that by another summation, t from 1 to capital T over 2 of x 2t minus 1. This is the odd bits. E, well, we'll say exponential of minus 2 pi I j. Oh, I forgot the t over here. T j t. I guess the order doesn't really matter, but I'll try to keep it like this. T over 2. All right, so what did we do? Well, let's go back and look at the original discrete Fourier transform that I wrote somewhere up here. Okay, it's the thing that I kind of circled in green. So all we're doing is we're taking the index t and we're splitting up the odd bits and we're splitting up the even bits. So what happens is we effectively just replace, we're replacing t with like t doubled in some sense. So what we get now is we're running t just from 1 to t over 2, which changes our denominator and things a little bit, but more or less everything's the same. The idea is that we've just taken that giant sum for our DFT and split it into two pieces, the even bit and the odd bit. And we will denote the even bit as EJ. And we're going to denote the odd bit. Well, first we have to multiply by that coefficient, which is minus 2 pi IJ over T. And we're going to multiply that whole thing by OJ being our odd bit. All right, so we've split it into two pieces. How does that help? Well, it turns out that each of EJ and not theta, so used to writing theta, OJ are DFTs. They're discrete Fourier transforms of T over 2, of size, we'll say T over 2. So the point is that I've turned one DFT of size T into two DFTs of size T over 2. And I can keep doing that. Hence, we can continue to split EI and or EJ and OJ into DFTs of size T over 4 and so on. Right, so does that actually help at all? Well, yeah, it kind of does, because if computing a discrete Fourier transform takes t squared time, then just to give a quick example, one DFT at size t requires, let's say, about t squared time. But two DFTs at size t over 2 require, well, what? 2 times t over 2 squared, or t squared over 2 time. Hey, that's kind of neat. So we've basically cut our runtime in half just by doing one split. And if we were to keep doing this again and again and again, those halves kind of add up, and we end up with a log 2, kind of. There's actually one more thing we can do to make this even better. So what I'll say is even better, ... is that there is some redundancy in our calculations. Even better, it turns out that the square root of t times the discrete Fourier transform at j t is going to equal, well, it's going to equal what I wrote before. It's going to equal ej plus e to the minus 2 pi ij over t oj. And more interestingly is that the square root of d at j over t plus 1/2 is going to equal ej minus e to the, I think it's the same thing, yeah, 2 pi ij over t times oj. So in some sense, if we split our data, we get 2 Fourier transforms or 2 DFTs for the price of 1. All right, so what are we doing here? Well, in summary, again, the idea, because I feel like there's a lot of equations in this lecture, and I want to make sure that it's kind of clear that you haven't lost the plot, right? You haven't missed the forest for all of the trees that we've had to fight our way past. So in summary, what are we doing? Well, we're considering our data represented as a periodic process that I wrote in green here. I highlighted it in green, but more so the idea is that we can use regression to try to find significant frequencies in our data. Now, we don't want to do that by hand, but it turns out that doing regression on a time series data like this is equivalent to computing the discrete Fourier transform. And then the question is, well, how do we compute the discrete Fourier transform? Well, we can do that in many ways. If t is not too big, we can just brute force it as by multiplying the transformation matrix by x, that is our data x, by the transformation matrix w. But if we have a larger data set and we want to be a little bit more clever, we can use the fast Fourier transform. Now, I presented one way of doing the FFT here, which is this divide and conquer method. It works when t is a power of 2. Obviously, your time series data may not be a big power of 2. There are other fast Fourier transform methods out there and different things. I'm not going to get into all of them because that's not really the point of this course. But I thought it was worthwhile to take the last part of this lecture just to explain what's actually going on here, because I think it's kind of neat, this idea of dividing and conquer in order to compute the Fourier transform. So that takes us to the end of what I wanted to talk about today. In the next lecture, we get to go into something even more interesting, which is the spectral distribution and the spectral density. And what do you know? We're going to get some theorems, and it turns out our good old friend, the AutoCovariance, will be back again, because we're going to be able to write our spectral density in terms of the AutoCovariance. Like everything in this course, the spectral density, as well as everything else, is just a function of the AutoCovariance. And we will look at that in the next lecture. So see you then.